final talk for the session is an early career talk, and it's by Chirayu Haryan from Intel.
Hi everyone. So today I'll be presenting our tool called DPFramework, which is to generate highly efficient CPU implementation from pseudo-code for dynamic programming algorithms. My name is Chirayu Haryan, and this project is by my team from Parallel Computing Lab, Intel Labs. So dynamic programming algorithms is widely used in computational biology. There are problems like sequence alignment, RNA folding, HMM that use it. These problems are compute intensive and benefit significantly from optimized implementation. However, writing optimized implementation is really challenging. Why is it challenging? It requires deep understanding of one, low-level optimization techniques like cache blocking. Two, there are multiple levels of parallelism like multi-threading, vectorization that you have to use. And after you have implemented all that, sometimes you have to again fine-tune your program to depending on the system that you're running on. So that is called architecture-specific tuning. And because of all these reasons, developing high-performance implementation can easily take months of efforts. So our solution, we are building a framework for generating optimized code. We propose a deterministic, rule-based approach that generates highly optimized implementation and with negligible programming effort. Our goal is to empower researchers to focus on algorithms and not the low-level code details. So this tool DPFramework is part of our bigger effort called Openomics. So Openomics is our performant and easy to use platform for biology algorithms. At a higher level in Openomics, you have single pipelines that you can directly use. If there are users who want to create their own pipeline, custom pipelines, we have something called as Openomics toolkits, which has Dockerized workloads that you can combine to create your own pipelines. And finally, we have building blocks, which contain all the fundamental biology tools like DP chaining, sequence alignment, FM index, and this is where our DPFramework fits in. So this slide gives the overall idea about our framework. So our goal is to, again, generate high-performance code with minimal effort. And to achieve this goal, we have developed a domain-specific language, which is one, easy to use. The conceptually, it is as easy as writing a pseudocode. Two, it is deterministic and precise. So on our DSL, it's very easy to use rule-based translation to generate optimized code. And finally, three, it's flexible so that we can support various use cases. So to understand the framework, I'm taking sequence alignment problem as a proxy. So in this problem, as you all may already know, that we have two sequences that we work on. The goal is to identify similar regions by aligning character in the sequences. And because we can have multiple kind of alignments, there is a way to score these alignments. And based on the score, we can decide which alignment is good and bad. So a very popular algorithm for solving sequence alignment problem is Smith-Waterman algorithm. It's a DP-based algorithm. So in DP algorithm, the main crux is its recurrence relation. And what is a recurrence relation? It's basically a formulation where you break your big problem into sub-problem and use the solution of this sub-problem to solve your bigger problem. So in implementation, we generally maintain a DP table which holds the solution for all the sub-problems. And then once the DP table is completely filled, we eventually find the solution for a bigger problem. So this is how the naive implementation looks like for the sequence, for the Smith-Waterman algorithm. As input, we generally have a list of pairs of sequences that we want to compute on. So in a for loop, we go through this list of sequences. We read the two sequences in the body, and then pass these sequences to our recursion function to get the final score. The recursion function implementation basically has two for loops that traverse the TP table, the 2D TP table, and inside the for loop we have the main recurrence relation formula. So it's fairly easy to write this implementation, but the problem with this is that we don't get the best performance. So if we want to have the best performance, we have to add some optimization technique. So I'll go through a few optimization techniques that are used. One is vectorization using AVX. So AVX is a feature which is there in modern CPUs, especially from last decade, which is basically it provides you special instructions that you can use to perform operations on multiple data simultaneously. So you can think of, in general, if you want to do add operation, it would be adding just 2 numbers. With AVX add instruction, you can add 8 numbers at the same time. So when you want to use AVX to optimize your code, you would write your recursion function using AVX instructions. So this is how the code would look like. But now instead of doing one DP table at a time, internally you will be able to compute multiple DP table at the same time. Further, the another popular technique is using multi-threading, where you offload your pairs to different cores, and all these cores work in parallel. So you get a different, more level of parallelism, and this improves your performance. There are other techniques like register tiling, loop unrolling that also goes underneath to get the best performance out of your implementation. But after doing all that heavy lifting, we do get performance benefits. So this is the naive code, the simple code that we had written, and for a certain data set, it took around an hour to complete. For the same data set, with the optimized code, we were able to complete under just 4 seconds. However, there is a lot of coding effort that goes. So the key kernel, the Smith-Waterman kernel in the naive code was just 20 lines. And in the optimized one, it becomes around 440. So there is a lot of coding effort that is required. So that is why we bring in DPFramework. So our main key idea is that ideally we would want to just take the crux of the DP algorithm, that is the recurrence relation, and transform it to an optimized code. So we have seen that there are many different classes of DP algorithm. So we first identified a subclass of DP algorithm which is very relevant in the area of computational biology. And this class of DP algorithm looks something like this, where we have a pair of sequences as input. We are dealing with one or multiple 2D DP tables, and the recurrence relation is such that a cell in your DP table is dependent on the left neighbor, diagonal, or the top. So this is the kind of dependency that we have in this subclass. And there are many examples that belong to this subclass of DP algorithm, like edit distance, Smith-Waterman, Needleman, Wunsch, HMM, and multiple flavors of Smith-Waterman. So on top of building a framework that handles this subclass, we also aim to support multiple heuristics, like banded DP computation and early exit criteria. I'll go into these details in the next slides. So when we studied multiple highly optimized implementation in this subclass, we identified that there are many common optimization techniques that are there in all these codes. So we were able to pull out these common optimization techniques and put it as a fixed part of the code, which is going to be there in all our generated files. And we also were able to put some placeholder for the problem-specific code. So problem-specific code would include initializing the DP table, because some problems will have one DP table, some could have 3 DP tables. Another important placeholder is for calling the recurrence relation. So for filling this placeholder, we went through multiple challenges. So I'll go through some of these challenges in the next slides. So first is, how do we call the recurrence relation? So what we have observed in this highly optimized code is that the main recurrence relation is generally vectorized in all the DP codes. So now we don't want the user to be very overwhelmed with the AVX related techniques. We want to provide a user an easy way to express their algorithm through scalar style pseudocode and generate the vectorized code on our end. So to do that, we first came up with a DSL for defining the recurrence relation. And this DSL, this is a basically domain-specific language. Basically, it is a set of instructions, and this set of instructions are sufficient to write any kind of recurrence relation. And the key feature of this DSL is that it is one AVX architecture aware. So you may know or not know, but there are CPUs which has different kind of AVX, AVX2, AVX 512. So AVX 512 is better than 2. So when you use our DSL automatically detects which AVX unit is there in your CPU and uses instructions for that. So that is what a user does not have to worry. And second benefit is data type agnostic. So if you have done AVX programming, you may know that even for simple add instruction, you have so many different options. So there is add instruction for int 8-bit integer, for 16-bit integer, for float we have different add instruction. So when the user is using our DSL, they do not have to worry about the data type, we handle it at our end. Second thing, to complete the recurrence relation translation, we needed a way to define the DP tables. So some problems, as I said, could have only one DP table, some could have multiple. So in this example, we have 3 DP table, and to denote that, we have notation that we tell the first DP table as A of 0, A of 1, and A of 2, which is very general in computer science. Also, we identified that the DP tables could have different kind of dependency. So here the DP table, the current cell is only dependent on the left cell. Here the current cell is only dependent on the top, and here the current cell is dependent on the left diagonal and top. So we have named these types as type 0, type 1, and type 2, and based on these types we are able to add multiple optimizations. So after using the DSL and this table notation, the recurrence relation in a DSL will look something like this for Smith-Waterman. We'll see this recurrence relation again, where I can show you how the pseudocode and the recurrence relation would look like. So the other challenge was we wanted to support heuristic. So one very popular heuristic is banded computation, where the idea is that you don't compute all the cells in the DP table, you only compute DP table around a certain band. And the main idea is that we believe the ideal score for the entire problem lies somewhere in between and not on the edges. So this helps in getting good performance. So this is one feature that we wanted to add. So because of the structure of our DP framework, it was easy to first start with this adding heuristic. So we were just easily able to add right place for the heuristic code where it would come. But how do we fill that? That is another challenge. So as you know, like I was discussing, that in the highly optimized version of the code, your recurrence relation is vectorized. So it means that when you're writing your recurrence relation, you're thinking you're filling only a single DP table. But internally, multiple DP tables are computed. Now, all that details the user is unaware about, but we have to handle. So the challenge here is that when you're doing banded computation in a AVX kind of scenario, the band size, if all the DP tables that you are working on and the band size is same for all the DP table, it is fine, it is easy. But the band size, if it is different, so let us suppose we are working on this particular row, this cell is active because the band is still in the end. But for the other table, the band could have ended already. So this cell is not needed for the other table. But when we are computing the cell, we should ensure that we do not write into the other DP table. So to take care of all these things, we had to handle it in our framework. So our solution was, first, we were able to implement a generic masking logic by that in our templates itself. So because of which the user does not have to worry about doing the masking. To provide the band boundary logic, that how the band is computed, we are able to provide user to write that logic using our DSL. So how we would use the DP framework? So the step 1 is to first write the recurrence relation. So this is how the recurrence relation would look like. So this is the pseudocode. This is our recurrence relation in our DSL. You can see that I'll just go through this one line. Here you are finding the substitute value based on if A is equal to B, the substitute value is match, otherwise it is mismatch. In our pseudocode, we first do the comparison using compare equal, A equal to B. If that is equal, the assign if will assign match, otherwise assign mismatch. The max and add instructions are very easy to understand. Second input would be the configuration file, which will include all other details based on our DP problem, like how many number of tables we have, what are the type of tables, what is the data type of the DP table, and so on. Using all these details, we are able to generate the optimized code, and this is finally how the performance and the code size will look like. So performance wise, the optimized code in our previous slide was roughly under 4 seconds, and our DP code or generated code is also not very far away. It's again 4.22. And coding effort wise, so this shows what is the code effort for writing the key kernel. In the naive it was 20 lines, and in the optimized version it was around 440. In our DP framework, you don't really have to write any code for the key kernel, you have to write the pseudo code that in our DSL. So I've included that and the configuration files. So it is roughly 26. And with just this much, you are able to generate as performant code as your optimized one. So this framework is soon going to be available on our OpenOmics platform. We have posters on the Openomics platform at poster 26, and the DP framework is also available at poster number 13. Thank you.
So my question, I have two questions. First is whether the optimization that you have showed, is it just specific to Intel family of chips?
It is specific to CPUs, not Intel CPUs. x86 CPUs, it should work for any x86 CPUs.
Okay.
So even AMD,
we can also
work,
see the same
which has AVX to AVX 512.
It will not work on the RISC part. The
Right,
RISC CPU.
right.
Okay. The second question is, I would want to ask about the traceback part. So the traceback part is totally linear compared to the matrix computation. After the matrix computation,
Right.
what's actually happening in the traceback part?
So right now we have just added the code for computing the DP table. The traceback part is left to the user, because sometimes user may want to do it, or sometimes they do not want to do it. So that is left to user, and you can use the DP tables. We have that output. You can use them to trace back the solution.
Okay. Okay.
Yeah, I have a more practical question. So these AVX, optimizations have not caught up. One of the reasons being that they tend to heat up the CPUs and the clock is downgraded so as to keep this in CPUs functional. But you have shown only for one instance how it is working. Did you keep on burning and see, whether it could retain the performance?
Okay, so we have tried this on multiple flavors of Smith-Waterman as of now. This is a work in progress project. So we have tried multiple variants where we do see performance benefit of using our framework.
No, I'm saying that when you sustain the burning, so this is one instance, right? So
right.
Which means in a burst you do the computation, the CPU comes down. So there's no heat issue.
Okay.
But you constantly run the AVX computation, which means the entire microarchitecture of the CPU is constantly running at a very high clock speed.
Right.
It heats it up,
right.
and the clock speed is downgraded to manage the heat.
Right. Okay. So for the data that we tried, as you saw that it was only completing under 4 seconds. For the throttling issue to happen, I guess we'll have to try it out. Right. 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 Sure. I'll note it.
A question here. So all these topics was discussed around CPU and its optimization. So along with CPU optimization, what is the load that the memory will memory will play? Because we are computing multiple DP tables here, right?
Right.
So tracing back, it should store the DP table somewhere.
Right. So when we have written our implementation, the fixed part of it, it is such that it is written to optimize your memory utilization also. Because without optimizing on the memory part, you will less likely get such good performance. So our template, the good part is that templates, the fixed code of the framework is written such that it handles the memory part for you. So you don't have to worry about it.
Okay, so the memory optimization is
put in place.
Already involved in the framework.
Right.
One of the hallmarks is also the memory, right? You have. So is there any improvement in the storage of the memory, or is what I meant is not the CPU's memory. I mean the space required to store the whole table.
Right.
It is anyway there, right? Or is there any improvement or less space required because of this optimization?
Right. So there are some optimizations where, for example, let me show you. So there are some DP tables, right, where you are only dependent on the top cell. If I'm only dependent on the top cell, I don't really need to maintain the cells above it. So such optimizations are already in place in the framework, and it is generally used in other optimized implementation also. Even for this one, if you see, the current cell is only depending on the topmost row. So the other rows we don't really need to maintain, and this is one common technique that is across all these problems that we detected, that they are only maintaining 2 rows at a time. So you don't need to, so that way you save on the space also, and that brings that memory optimization.
All right, thank you.
Thank you.
One question is, when you say that with this AVX optimization, we have memory optimization as well, but is it like with naive, you let's say need X memory, but now you are computing 8 tables. So now instead of using 8x memory, you are using 2x, or is it like only the x amount of memory that naive was using, or even better than that?
Right. So as I said, so in the naive case, what would happen if I was implementing this DP table? I would have declared the complete n cross n table, right? One key optimization, as I said, that we only maintain 2 rows. So that because of which you are able to now save on the memory part. So this is one part which is already there in the template of our code generator. So that is how we save on the memory.
But I mean, that one can do with the naive algorithm as well. It's
yeah,
like
sure. Yeah. So when I started with naive, I started with a plain implementation. You can always add such implementation. Like you can always start with reducing memory, then you can add your multi-threading eventually. So naive was one like plain simple how a like very new user would write a program.
Okay.
Yeah.